Well, welcome back to part 2 of the series on building a mixing desk. Today we're going to look at the power supply. This is the basic circuit that I'm going to use. This is a circuit that I have sort of developed in advance. I won't bore you with the details, but it's an adaptation from a circuit in the datasheet of the LT1935 switcher chip. Now this chip is a fairly simple switch mode power supply controller chip from Linear Technology. It's a 5-pin SOT23 package, so the physical size of it is about 2mm by 3mm with five electrical contacts. And inside it's got a switching MOSFET, quite a high current MOSFET, and a PWM generator with an error amplifier and a feedback loop that can be used to control a switch mode power supply. So the way this circuit works, let's start at the input. We get 12 volts coming in. This power supply will have some series resistance because it'll be on the end of a wire. It'll be an output from a 12 volt wall adapter, something like this. This is a 12 volt 2 amp power supply, and it'll be something not dissimilar to this that will drive this circuit. And in order for this circuit to have lots of current when it switches, we put a local capacitor here. This capacitor means at this point now AC has a very low impedance, and we'll very likely put a ceramic capacitor in parallel. So this will be an electrolytic capacitor which will have about 30 milliohms of series resistance inside the capacitor, just due to the chemistry of the capacitor. And that 30 milliohms is essentially in series with the capacitor, and means that if you were to demand an instantaneous current on this point in the circuit, that 30 milliohms would limit how much current this capacitor could provide. So it essentially limits the upper frequency of the AC ground that you're creating at this point in the circuit. So if we put a ceramic capacitor in series that might have just a few microohms of series resistance across this, then the ceramic capacitor handles the high frequency and the electrolytic handles the low frequency. Okay, so we have a power supply to the chip. That just powers the internal electronics within the chip, allows it to generate its reference frequency, it allows the PWM generator to work, the error amplifier to work, and so on. It also has an enable input, which in this drawing I've just tied high. You can also have a resistor from the power supply to enable with a capacitor to ground, which creates a ramp at that point in the circuit on power up, which is a soft start circuit for this, which I will most likely use because it limits the inrush current on startup. This is the switching node. Internally within the chip there is a MOSFET to ground here on this switching node. So if we just ignore everything under my hand and just look at this part of the circuit, what this will do is, at a switching frequency of 1.2 megahertz, it will switch this point to ground for, say, 20% of the duty cycle of that 1.2 megahertz frequency, which will start to charge up this inductor. Now, if you short out this side of this inductor, what you've done is connected your input voltage directly across the inductor. Inductors being what they are, that will begin to create a magnetic field in the core of the inductor. Now, if you just left that forever, the core of the inductor would saturate, and at that point the only thing limiting the current through the inductor will be the DC resistance of the windings, which in this case will be very low indeed. So that would essentially be a short circuit across the power supply, which would then cause the inductor to heat up and pop. However, we're only connecting it for just the briefest amount of time, so the core will not saturate. We deliberately set it up so that that magnetic core will not saturate in that time. So there'll be a current ramp. The current will start at 0 when you close the switch and slowly ramp up. And at some point during that current ramp, we're going to release the switch. And what will happen at that point is that magnetic field in the inductor suddenly hasn't got anywhere to go. There's a current flowing, and then we just release the switch. And what happens with an inductor is it really wants the current to keep going. So what it will do essentially is do anything it can to keep that current flowing. So just as a capacitor resists a change in voltage by supplying current, an inductor will resist a change in voltage. An inductor will, let me start saying that again. A capacitor will resist a change in voltage by supplying current. An inductor will resist a change in current by supplying voltage. So essentially you can think of it like a transformer. There's a magnetic field here in that core, and that field is going to begin to collapse, and as it does, it induces a voltage in the coil. And that voltage adds to the input voltage. So what you end up with now is the voltage across the inductor, caused by the collapsing magnetic field, added to the input voltage. So this node, when you release the switch, goes from ground when the switch is closed, and then up to some voltage greater than the power supply voltage. And that can be really quite high voltage depending on the topology. You can get boost ratios out of these things that can get you up to nearly 100 volts from very low voltage input. And what's going to happen, this point in the circuit is going to be sat at 18 volts eventually when the thing's in stable state, but initially if you just switched this on without any switching at all, then the diode would conduct and this point would come up to 12 volts and charge up the capacitor. So we could say the steady state of this circuit is with 12 volts here, minus the diode drop, so say 11.7 volts. When we switch this to ground, this point becomes ground, and so this diode is reverse biased, so no current flows from this point. This point is still at 12 volts. Any load will slowly start to discharge this capacitor, so this voltage will drop just a little bit while the switch is closed, and current will flow up and charge the inductor. Then we release the switch. This point here now flies up to the power supply plus the voltage across the inductor. And that means that this voltage is now going to be higher than 12 volts, which is the voltage here. So this diode will start to conduct and will start to pump current through this diode into this capacitor. Now, if we just let that run without any feedback at all, this is a way that the chip can monitor the voltage, but we'll come back to that. If we just let this run, this point here would float up to really quite a high voltage, and the voltage here would be dependent on the duty cycle of the switching. So if it's going at 1.2 megahertz, if this was only closed for 1% of the time, then this would only be a little bit higher than the input voltage. If this was closed for 50% of the time, then this could be significantly higher. And actually the ratio, the voltage here is just entirely dependent on the ratio of the switch and the load. Those two things, the amount of load current and the duty cycle of the switch, sets the voltage here. So what the chip does is it works to try and set a predictable voltage here. Now we want 18 volts, so what we're going to do is feed a portion of that 18 volts back to the feedback node. Now this feedback node will always be about, I think it's 1.26 or something volts. There's an internal voltage reference, and it has an error amplifier that compares the actual voltage on this pin to an internal reference voltage, which I believe is about 1.26 volts, but you have to check the datasheet of the chip to be certain. So what we do is we say, well, if we want 18 volts here, that means we want 1.2 volts here, 1.26 volts here, and so you set up this divider ratio so that when there's 18 volts here, there's 1.26 volts here, and the chip adjusts the duty cycle of the switching in order to make this voltage 1.26 volts, which by extension makes this 18 volts, and that's how it regulates. Now, as I've already mentioned, while this switch is closed, the whole load drawn on this circuit is being supplied by this capacitor, which, okay, it's running at 1.2 megahertz, so and if it's only, say, 20% duty cycle, then this cap has only got to supply current for 20% of the duty cycle of 1.2 megahertz before it's charged back up again, but there will still be some ripple. It will still discharge a little bit during that switching cycle, and as you're pumping current in and charging it back up, it will overshoot 18 volts very slightly on the up cycle. So this point here is going to be quite noisy. It's going to have something close to a sawtooth on it, or a triangle waveform, on that voltage, which will be at the switching frequency, so that will be 1.2 megahertz. Which is convenient for us because that's high enough that it's quite easy to filter out. Okay, so that's the top half of the circuit, and that's a fairly understandable circuit. So this is a linear regulator which just drops the 18 volts down to 15, and also and means that our output is now below the minimum. So if that's our 15 and that there is our nominal 18, we get rid of all that sawtooth waveform and we're left with a nice stable DC somewhere below. Now there'll be some coupling across because that is quite high frequency, but we can get rid of that with some series inductors, which I'll show you in a minute. The clever part is this bit of the circuit, the minus voltage. Now, what this can also do is produce a negative voltage. So the way this negative half of the circuit works is actually surprisingly simple. On the positive switch cycle, this point here goes to really quite a high voltage. It will be going to 18 volts plus the voltage drop of the diode, which in this case will be 0.3 of a volt. Because at that point this will start to conduct, and this point here will clamp at close to 18 volts. So this point here will go to about 18.3 to 18.5 volts. When it does, this point here is close to 0, so we end up with 18 volts across the capacitor, with plus 18 here and 0 here. Then when we close the switch, this point goes down to 0, but there's still 18 volts across the capacitor. So this node must go to minus 18 volts, which reverse biases that diode and forward biases that diode, because this point here is now below this point here. If this was at 0 and we drop this down to minus 18 volts, current would flow through this diode but couldn't flow through this diode because this is at 0. So if that's at minus 18, then that's reverse biased. But if that's at 0, that one's forward biased. You see, higher voltage on this side allows current to flow in this direction. So current will flow through this diode and try to equalize the voltage on across this capacitor by transferring charge from this capacitor to this capacitor. And that's how it works. So that's the fundamental principle of a charge pump. You charge up one side of a capacitor to a voltage, then you pull it to 0. That necessarily means the other half of the capacitor must shoot down to a negative voltage. And then you have the diode to portion that charge through in chunks and smooth it out on this side. It's a very similar idea to this circuit, where you store energy in an inductor and then pump it through a diode, one switch cycle at a time, into a reservoir that then is your power supply. Except instead of using an inductor, we're using a capacitor. But the operating principle of the circuit is very similar. This point goes up to 18.4, 3 or 4, charging up the cap. During that half of the switch cycle, this point here is at 0 volts. Then you take this to 0, which means this necessarily goes to minus 18.4, forward biasing that diode, essentially subtracting charge from the capacitor, but you're essentially adding charge from ground onto the... I've drawn that cap the wrong way around. This is the negative, and this one is the positive. You're charging up the positive half of this cap from ground, essentially, by subtracting electrons from the... Well, obviously, we're talking conventional current here, not electron current, but yeah, that's how it works. I think I've explained that reasonably clearly. So you'll end up with minus 18 volts here, and you get minus 15 volts on the other side of the linear regulator. Again, this point here will have switching noise on it, because the same deal I was saying where you're going to have a ripple, the same is true here. This is only supplying power to the circuit on every time the switch closes. So where this one supplies current when the switch opens, this one supplies current when the switch closes. So there'll be ripple on both, and this one will be out of phase with this one, which actually means it's really bad to power analog circuitry, because... Okay, let's explain this in a bit more detail. The reason we have two power supplies to an op-amp, we have an op-amp with a plus and a minus, minus 15, plus 15, in and out. If these power supplies have got some noise on them, but that noise is exactly in phase, so let's say the positive is doing this, and the negative is doing this, the average of the two is always 0, because this is always the same distance. So even though there's ripple on each power supply, at any given instant in time, the output doesn't move, because the output is being generated by a pair of transistors that go between the rails. And so because they're moving in unison, the output stays in the middle. That's fine. If you've got two power supplies that are doing this, where one goes up and the other one goes up as well, out of phase, the average of the two is now doing this. Instead of being an average that's flat through the middle, you've got an average which is sawtoothing up and down. And that's really bad. And so what we need to do is make sure we get rid of all of that noise so that it doesn't appear on the output. And that is the point of these two regulators. Lastly, if we really want to make sure we don't have any noise on these outputs, bear in mind this is 1.2 megahertz, which is a very high frequency and therefore consequently quite easy to filter out. What we'll do, this is our LM7815, which is a 5-volt linear regulator. The in, common ground, and a V out. Now you must have, as a minimum, those two capacitors either side. It needs those for stability. Without them it will tend to oscillate. And there's usually a specified minimum output capacitance, which is often of the order of 10 microfarads. Sometimes it's lower, but there's an internal feedback loop inside here with its own voltage reference. And without that output capacitance, that loop becomes unstable and has a tendency to oscillate. What we'll do is we'll put an inductor here. And another capacitor on this side of the inductor. And that's what's called a pi filter, because it's a pi shape. You know, pi looks like that when you draw it as a symbol. And this L and this C and this C create the roll-off. And so what we'll do is we'll put that roll-off at, say, 100 kilohertz. Now this pi section filter is a 3-element pi section, and the internet suggests that what you should have either side. So there's all sorts of online calculators for these things. It's far easier to just use an online calculator than it is to use the math, to do the maths yourself, and then simulate the results just to be on the safe side. Yes, I'm lazy. I'm very sorry. Let's say we're designing a pi section filter to have 100 kilohertz roll-off. Now this power supply has to be able to do 150 milliamps, which at 15 volts means you've essentially got 150 ohm load on there. Sorry, 150 ohm load is 100 milliamps. So the suggestion is that we need 477 microhenries and 10 nanofarads on each side. Now, we actually have ten microfarads here, and at least 20 microfarads here, but more likely probably 100 microfarads here by the time you've added everything up. Because bear in mind, this will be driving a whole load of op amps, and every op amp will have its own 100 nanofarad capacitor, and every 3 or 4 op amps I'm going to have another 10 microfarad cap. So if we now solve this pi section filter for a 100 kilohertz roll-off, we end up with an inductor value, which I'll go and work out. So, having run some simulations on this circuit, I've discovered that 500 nanohenries here produces really pretty good performance. Now, unfortunately, this type of circuit has an inevitable peak, which will look something like this. And that peak is the self-resonance of this circuit. And what we want to do is make sure that that resonant peak is well outside the audio band, so that all of the low pass filtering in the rest of our circuitry will filter that peak out and make sure it never makes it to the output, should anything ever excite this power supply at that peak. Now, if that was slap bang in the audio band, it might well be that a load on this, which was varying at that frequency, could get this thing oscillating, so we want to make sure that that's never going to happen. So I want that peak to be somewhere around 25 to 30 kilohertz. And that is determined by the ratios of these components. So 100 microfarads, I actually went with 20 microfarads on this side to give the LDO some more stability. And 500 nanohenries produces a peak at 25 kilohertz. And at 1.2 megahertz, we are 70 dB down. So that should produce an extremely clean power supply. Incidentally, this is a technique that we use at work on all of our power supplies, except that we use a two-stage filter with a cap, an inductor, a cap, an inductor, and another cap, and we have one of those either side of the linear regulator because we are working to ridiculous resolutions and noise floor requirements, which would, even the noise that would get through that filter, which is going to be a few microvolts, would be too much for the circuitry that we do at work. So we go to extreme measures. So I think it's time we looked at a simulation of the whole power supply and had a look at some of these voltages and waveforms. So here is that simulation of the pi section filter. I'm using LT Spice for this, which I find to be a very good package. So I've gone, you add your components from up here. You can see that we've got resistor, capacitor, inductor, diode, and that's for all the other components, and that brings up a sub window. So I've created a voltage source which is set up with an AC amplitude of 1. You right click on a source to modify it. In this case it's set up with an AC amplitude of 1 volt, and we've gone for 20 microfarads, 500 nanohenries, 100 microfarads. We've set up an AC analysis, which you can right click on to modify, and I've just gone for a decade with 1,000,000 points per decade to go from 1 hertz to 100 megahertz. I think a gigahertz actually, yeah, a gigahertz. And so you can see we've got, if we look at the scale, it goes down to -200 and up to +40. So this resonant peak is at +40 dB, but its center frequency is 22.5, 23 kilohertz. Fine. Handy tip, this no magnification button, extremely handy. And then we look at 1.2 megs. Close enough. -70 dB. Right, let's look at the power supply in total. Okay, here we are simulating the entire circuit. I've got it pretty far zoomed out, so it's a bit difficult to see, but you can sort of see that is the same circuit. I'm using linear tech regulators rather than the 7.8 and 7.915s because they're in the library. So that's this, and there's our pi section filters. And here is the running simulation. So the input is 12 volts, pretty noisy, but I'll get on to why in a minute. There's our plus 18 volts out, and our minus 18 volts out, still falling, takes a little while to stabilize. And there's our plus 15 volts out, and our minus 15 volts out, which are now stable, just. And there we are. So we'll let that simulation run for a couple of minutes until it's fully stabilized. In fact, to be honest, it's stable now. So let's have a little look at what we've got coming out of here. So here is the positive half. You can see there is some noise on the 18 volt supply, although not much. Looks like maybe 50 millivolts, probably less. And the 15 volts, I'm expecting to be really, really very clean indeed. Let's get some more zoom in on that. Okay. Yeah, I think we're alright, don't you? Let's go again. Yeah, that's okay. Nothing wrong with that. That's under load, by the way. So that's how much switching noise is getting through into 150 milliamp load, which is the full rated load of the power supply. Right, let's have a look at the negative supply. Again, you can see there's noise on the rail, but on the 18, but the 15 volt, clean as a whistle. I mean, that's 10 millivolts on the whole scale. Actually, slightly more than that, but even so, it's clean. Well, you can see there's a little bit of noise there, but significantly less than a millivolt. It's a few microvolts. So I think I'm going to call that good. So there's the power supply. So I'll look at that in a little bit more detail. So we've got the LT 1935 with the soft start that I mentioned on the shutdown pin, that's here. We've got our input capacitor, and the resistance of the wires from the power supply is included in the simulation. We've got our charge pump with our 3 charge pump diodes. Sorry, my camera's hunting for focus. We've got our 18 rail, and we've got our -18, and then we've got the positive linear regulator. This is actually an adjustable regulator, it's just what was in the library, with the pi section filter on the output. And the negative regulator, again, much more than we need. I'll use something much simpler in the real design, with its pi section filter on the output. And there's the power supply.